Welcome to the 12th lecture from chapter 8. We are studying logical effort and we'll continue studying the same topic even in this lecture. A quick recap from the last lecture. We studied that logical effort composed of various components like logical effort, the same, electrical effort, and the path effort. In this lecture, we will study logical effort in a bit more detail. Logical effort we studied in last lecture is defined for a gate, and if it is for a gate, this is the input capacitance of that gate divided by the reference capacitance, where the reference capacitance is from a symmetric NOT with M is equal to 1. The capacitance in the numerator comes from a symmetric NOT whose M is equal to 1. Scaling factor is 1. In today's lecture, we'll calculate the logical effort of a NOT gate which is symmetric and has a scaling factor of 1, the same as reference. If it is the same as reference, of course, the answer would be 1 because the logical effort of this gate is 1 because the numerator and the denominator are the same. But if we compute logical effort for a NOT with scaling factor 2, this means that this PMOS is 2 times R. If it is for M is equal to 1 and it is symmetric, then PMOS is R times larger compared to the NMOS. If NMOS is 1, PMOS is R. But if it is for M is equal to 2, PMOS is 2R and NMOS is 2. And the ratio of course remains the same. PMOS is R times larger compared to NMOS. And they both are scaled to 2. Here we have 2R plus 2, taking 2 as common, 1 plus R. This cancels with this 1 plus R and we are left with 2. So for a NOT with M is equal to 2, the logical effort for this NOT gate is 2. And let's generalize it. If it is small n, if n is any arbitrary integer, this comes out to be small n. Right, here is my eraser. Oh, I got it. I got my eraser. Right. And let's take a step further to find logical effort of a NAND 2 gate with M is equal to 1. NAND 2 is from the schematic CMOS schematic for a NAND 2 is drawn like this. Right. And if it is symmetric, we have already studied that these two transistors has to be R. The aspect ratio is proportional to R, where the aspect ratio of these two series connected transistors have to be 2 because they are always in series, and in the worst case they both conduct and the resistances they come in series. So to have a delay that is equal to the delay of a NOT, they have to be 2 times in size. We have already studied that. And if there are 3, the aspect ratio of each would be 3. So how would you write G for this? The logical effort G for this NAND 2 gate, which is symmetric and has M is equal to a 1. Right, the PMOS is R, the NMOS is 2. For any input, the PMOS is proportional to the aspect ratio of PMOS is proportional to R. The aspect ratio of NMOS is proportional to 2. So this is R plus 2 times the gate capacitance divided by the reference R plus 1 times the CGN. CGN always cancels, therefore most of the times we don't write it. So this is R plus 2 over R plus 1. This is the logical effort of a NAND gate which is symmetric and has a scaling factor 1. What's about the case if this NAND has a scaling factor 2? We have already studied that. This would be 2, this would be 2, this would be 4, this would be 4. So in the worst case, it would be 2R plus 4 instead of R plus 2. It would be 2R plus 4. So we can take 2 as common, R plus 2 over R plus 1. So the scaling factor always multiplies with the aspect ratio, with the G, the logical effort that we compute for M is equal to 1. In general, if it is N, we'll multiply it with N. Right. Going back, not going back. If it is NAND 3, what happens if it is NAND 3? Oh, for NAND 3, we'll have one more transistor here, and we'll have one more transistor here. This is also 4. Maybe let's do it for M is equal to 1, which is R plus 2 over R plus 1. This is 2, 2, 2, R, and R. Right. And this is not 3. This has to be so 2. This has to be 3. Because to equalize this fall time delay to make this fall time delay equal to the delay of a NOT, each transistor has to be 3 in size, 3 times in size. Right. So this is, in fact, this is instead of R plus 2, this is R plus 3. And if we have n such inputs, we'll be having, let's draw it again. Right. So what happens to this? These have to be R, and if they are N, they have to be, if they are, maybe this is, if they are K trans, if we have K inputs, all of it has to be, each and every one of these has to be K times 1, which is K. So this is R plus K, where K is the number of inputs for this NAND K gate. So making everything general for scaling factor N and for K inputs, this is like this. It's a pretty general expression where K is the number of inputs and N is the scaling factor. For N scaling factor and K number of inputs, this is the logical effort of a NAND gate. So we have made everything general. Now let's talk about the final thing for this lecture, which is the logical effort of a NOR gate. For NOR 2 with M is equal to 1. The schematic would be like this. Right. This is R, this is R. So they have to be 2R each to make this rise time delay equal to the delay of NOT. They have to be 1 because in the worst case, only one of them is on. So they are all 1. No matter how many they are in parallel, they are all 1. But if we increase these series transistors to 3, every one of these would be 3R. If we increase that to K, every one of these transistors would be having an aspect ratio K times R. So for this, we have to be, we will write G of NOR 2, which is symmetric with M is equal to 1 for P. For any of the inputs, maybe for this input 2R plus 1 over the standard 1 plus R, the reference capacitance. And following the same lines, G for NOR K, symmetric with M is equal to N, would be KR plus 1 over 1 plus R times the scaling factor. Right. So in the upcoming lecture, we'll keep on studying logical effort and we'll use this technique to minimize chain delays. Thank you.